I'm a scientist down at NASA's Marshall Space Flight Center, which is in Huntsville, Alabama. That center is better known for developing the Saturn V rocket and leading the efforts to go to the moon back in the Apollo era, and also now they're in charge of developing the Space Launch System and overseeing the development of the rocket that's going to take the America back to the moon in a year or so. Well, around the moon in a month or so, hopefully. But for Artemis 3, for actually landing on the moon in a couple of years. But we also do science at Marshall, and there's been a long history of doing what we call gamma ray astronomy. So I'm going to be giving a brief overview of what gamma rays are, what gamma ray astronomy, what we learn from gamma ray astronomy, why we think it's interesting, and then on to the mission that we have been developing to kind of extend our reach into this part of the universe, to be able to see the universe through the gamma ray wavelengths. So what are gamma rays? They are, of course, they're electromagnetic light, but they're at the highest frequencies of light. So if you think of radio being the long wavelength and going across the electromagnetic spectrum from microwave, infrared, visible light into the X-ray and gamma rays. So X-rays, everyone's familiar with X-rays. When we get just beyond the energies associated with, say, like a typical dentist X-ray, like about 10 times the energy of the X-rays that we would get in a dentist office. That's when we start. That's where we usually start considering those wavelengths. Anything higher than that in frequency as gamma rays. And so the wavelengths that we're talking about are down to the atomic nuclei, like that type of wavelength. What the reason why we're interested in this for astronomy is that gamma rays, unlike other types of light, can pass through lots of all the intervening dust and gas in the universe. Because it's such a high frequency and short wavelength, it can basically pass through most atoms and most molecules. Whereas optical light will get scattered, or other light will get absorbed, UV light or infrared light could get absorbed by dust and gas that's intervening between an object and Earth, the gamma rays can blast right through it. And so as a result, they probe, and they're also produced by the most energetic explosions and processes in the universe. So black holes, things falling into black holes, relativistic shocks, things like that. So they're tracers of very energetic things going on in the universe, and they can also they're not easily attenuated, so they give us a view of at the heart of galaxies and other types of energetic events. The one thing that is very good at blocking gamma rays, though, is molecular water. So ozone, for example, and fortunately for us, Earth has a lot of water in the atmosphere and a lot of ozone. And so this diagram in the middle here shows the wavelengths that actually make it down to the ground. Fortunately for us, visible light obviously can get through the ground. That's why all of our eyes have, most animals have been evolved to have eyes that can see in the visible light, or you can see the infrared light is there as well. Infrared makes it down further into the atmosphere, and then over in the radio waves. But everything else, ultraviolet, X-rays, and gamma rays, are very efficiently blocked by the atmosphere. And like I said, it's fortunate for us, because if that didn't exist, life on the surface of the Earth at least we would all get cancer very quickly from particles coming in and damaging our DNA and things like that. That's why also life was underwater for millions of years on Earth before plant life was able to produce oxygen and kind of produce a thicker atmosphere to allow surface life. So as a result, we have to go to space in order to observe gamma rays. To do any kind of gamma ray observations of the universe, we have to launch satellites, at least direct detection of gamma rays. And NASA has had, and the US government has had, a long history of doing this type of launching satellites with gamma ray capabilities. They first started doing it in the 60s because when we signed nuclear test ban treaties with the Russians, with the Soviet Union, that one of the ways that they monitored for those the compliance to those test bans is by launching a series of satellites with gamma ray detectors on them that could detect the gamma ray signal from a nuclear blast. And so they had both the Soviets and the U.S. had a constellation of these detectors that were always looking down at the ground in order to see the telltale sign, which was a brief flash of gamma rays. Now, what they ended up seeing, these Vela satellites that were operational throughout the 60s and 70s, what they ended up seeing was they saw these types of detections, these flashes going off on a regular basis, almost daily, but they were coming from space. They weren't coming from the Earth. And the reason they were looking in space too was because they were afraid that the Soviets would detonate nukes on the moon. So they had detectors pointing at the Earth and also into space. And lo and behold, they found a new class of astrophysical source that they had never that nobody had ever seen before. And these are called they were just dubbed gamma ray bursts because they didn't know what they were or where they were coming from. They just knew that every day they would see a flash of gamma rays from some randomly distributed some part of the sky, and that was a highly guarded secret for a while because they didn't want to release that they were seeing these things, and that would give the Soviets an idea of how sensitive their detectors were. But in 1977, this was finally released. In the early 90s or 91, NASA launched its first satellite to study these things. That was a project that was down at Marshall, and then we've had a series of missions that have refined the detection techniques and investigated these further. There's two in operation right now, two primary instruments with these capabilities, and Fermi is the primary gamma ray space telescope is the one that I work on at Marshall, and the mission that I'm going to talk about, StarBurst, is meant to follow on to Fermi. So this is what these gamma ray bursts look like. They are very bright and very highly variable. So these satellites would just see a constant running background of gamma ray radiation from the universe, and then suddenly you would see this huge spike in the signal and be highly variable, and then it would just go away and be gone. You would see these millisecond spikes within them. And so for a long time, people didn't know if these were coming from our solar system, if they were coming from the Milky Way, somewhere in our Milky Way, or somewhere out in the universe. If they were extragalactic, then that would mean that they would have to be incredibly energetic to be as bright as they were. So there was a lot of skepticism about their distance, and they were assumed to be very nearby. But that mission that launched in the 90s, they found that these things were coming from everywhere in the sky, just randomly distributed in the sky. And that meant that either they had to be really, really close by in our solar system or outside of the galaxy, because everything else in our galaxy is along the galactic plane. So we're in a disk galaxy, and if you look at the distribution of stars and things that could produce events like this, they would populate a specific line in the sky corresponding to the disk of the galaxy. And the fact that they didn't see that it was distributed throughout the universe, throughout the sky, meant that, like I said, they were either really close by or really far away. And it wasn't until 2008 when we launched a satellite that had the capability to narrow down exactly where these things were, that they were able to determine that, yes, they were coming from extragalactic sources and outside of our galaxy. Just to give you an idea, these detectors that flew in the 60s and all the way through the 90s, they could tell you where these things were coming from to like 10 degrees in the sky, and so, or like about the like the size of the moon. But within that radius, within the size of the moon, there are thousands, if not millions, of galaxies, right? So people didn't really know exactly where these things were coming from for quite a while, because they couldn't localize them. And so it wasn't until until 2008, when this new mission called SWIFT launched, that it had a gamma ray detector and an X-ray detector, and they could determine exactly the galaxy that they were coming from, and then people could go look at that with things like HST, with the Hubble Space Telescope, and see the actual explosion inside the galaxy. This is what they kind of look like also in gamma rays. If you were to integrate the total amount of gamma rays coming in from the sky and compare the explosion that we see, and you can see these things are incredibly bright, incredibly loud, and very easy to detect compared to this background. Now, one thing that was surprising was that if you were to take the duration of the signal that we see in gamma rays from these various telescopes, the distribution is very much bimodal. So there's one population that clusters around 2 seconds and another population that clusters around 30 seconds with a dip in between. And it's very pronounced early on that there seemed to be these two populations. Both of them were coming from outside our galaxy, but people didn't really understand what or know, what would be causing this bimodal distribution, these two different populations. But once we were able to pinpoint the galaxies that they were coming from, people realized quickly that that the types of galaxies that those events, the short ones and the long ones, were coming from were very different. The short ones were coming from what we call elliptical galaxies. These are galaxies that are round, they're red. The types of stars in those galaxies is very different than the Milky Way, like the galaxies shown on the right, these grand design spiral galaxies. The elliptical galaxies are galaxies that have all of their stars have already gone supernova. So all you see in them are very old, very low mass stars. So the higher the mass of the star, the shorter it lives, and when it dies, it explodes as a supernova. Smaller stars can live for a long time because they're burning their fuel less quickly, and as a result, they're kind of redder. They last for a long time, and you also get a lot of the leftover pieces after the stars go supernova. So at the center of a star, you have its core. When the star goes supernova, that core gets left behind as a compact object, and so these types of elliptical galaxies are filled with those types of objects. And those cores are very small compared to the size of the star. And so right away, people noticed that this dichotomy that you see between where the long ones are coming from, where the short ones coming from, pointed to something to do with those smaller cores, because the duration that you see in the gamma rays is indicative of the size of the object that's creating the explosion. So if you have a small compact object that's left over, and say two of those things combine or collide, then you can imagine getting a signal that's very short-lived compared to a supernova that is like this huge explosion of a massive star. You can see the picture on the right. This is a spiral galaxy that has multiple supernova going off at the same time. Like these things, these very massive stars don't live very long. They're like 50 million years compared to, like the Earth has been around for 4.5 billion years. But these supernovas that are much, much larger than our sun don't live very long, and so they kind of go supernova very quick, very often, and so you see a lot of this activity. And so the thinking was that, okay, maybe the short ones are coming from the merger of these compact objects, and the long ones are associated with supernovas in these types of spiral galaxies. And so that's what was shown here is this diagram on the right. It's like the short ones are like two objects rotating around each other, coming in and colliding, and then you get some kind of powerful burst of gamma rays. And theorists went off and worked on trying to figure out exactly how you get those gamma rays. It most likely involves the formation of a black hole, and then some kind of jet, like a material that gets superheated and shot out at the speed of light, and then that light, that material is producing the gamma rays that gets to Earth. And then for the long ones, the thinking is that it's a star that has used up its fuel in its inner core. It eventually collapses bounces and has a supernova, and in that core you get a black hole that's formed, and a similar process. That black hole superheats material and shoots out a jet that then is pointed toward Earth. That we see. So this is the fact that it's tapping into the energy of a black hole explains why these things are so powerful, yet they're so far away. These remnants that are left behind after a supernova, I refer to them as compact objects. We typically call them neutron stars. So the idea is that when the supernova goes off, the explosion is so powerful that all of the protons and the neutrons all the protons and the electrons that are inside the core, because stars are mostly made up of hydrogen with a little bit of helium, that the shock wave from the supernova compresses that material so much that all the protons and the electrons merge to form neutrons, and all that's left are neutrons. And so you get this super dense material that's left over in space. And these things are expected to have a radius of about 10 kilometers, but contain more mass than our sun. So it makes them incredibly dense. And you can see there's the artist's, depiction of a neutron star compared to a city, to Vancouver. And they're very small, but incredibly massive. So if you have two of those things hitting each other, it could release a lot of gravitational potential energy. So a lot of energy that's stored up in that material. So these are also thought of as the last stable type of matter before something collapses into a black hole. Now, in classical mechanics and classical physics, and what we call Newtonian physics, two objects could rotate around each other in space indefinitely. So you have two objects, you put them in motion, and they'll just rotate around just through the force of gravity forever. So if you have two binary stars, so like 50%, for example, of stars in the Milky Way are binaries. Like our sun is a single star, but about 50% of the other stars that we see in the night sky have a companion, and some have more than two. So the idea is that if the two stars are about the same age and they go supernova around the same time, then you potentially have a scenario where you have two of these neutron stars orbiting each other. And like I said, just from like Newton's equations, those two things would orbit each other forever. But Einstein showed in that with his theory of general relativity that these things, as they're rotating, they end up losing energy by radiating what we call gravitational waves. And gravitational waves are just essentially they're ripples in space-time itself. So these objects are creating disturbances within space-time, and that the space-time that's taking away energy from the system by putting the energy into the space-time, the fabric of space-time. And so this is something that he predicted in the 50s, I think, 50s or 60s. Well, 50. He died in 55, so it's before that. So 40s and 50s. But these ripples are so small, and because they radiate throughout the universe, that it was not something that could be experimentally measured for decades until the early 2015 was the first time we were able to measure this, and that was done using a new generation of detectors called gravitational wave detectors. And these are really fascinating instruments. They basically are a series of lasers that get shot down 1 kilometer lengths, and at the end of those lengths there are mirrors that bounce the lasers back. And so if the length of these path lengths of these lasers are exactly the same, then the laser light, when it comes back, will deconstructively interfere. So the light will basically phase in a way that you don't get a signal at the detector. So this light on the shown on the on the right here, you have one laser light, a laser going down one length, and then the other laser getting bounced and coming back. And when they combine, if these two lengths are exactly identical, the light cancels out, and so you don't get a signal. But if one of these lengths is slightly longer than the other, then you do see an appreciable signal. And so what this allows them to do is, as these gravitational waves, these ripples in space-time pass through the Earth, if they pass through one of the arms versus the other, you'll see that change in the path length. And the laser light is at such a high frequency that they can detect a change in that 1 kilometer length of down to the radius of a proton. So incredibly small variations in basically the dimension of space changing as these gravitational waves pass through the Earth. Now they have two of them because the other things that can change and cause noise here are like earthquakes and even highway noise and things like that. It all causes background in their system, because then these mirrors will shake and vibrate. And so because the gravitational waves are traveling at the speed of light, they have two of them. And so if they both see them at roughly the same time, but that they both see a signal at exactly the same time, at the same strength, then that allows them to determine that, yes, they just saw an astrophysical source passing through the Earth. As I said, in 2015 was the first time they turned these detectors on. They saw they detected the merger of two black holes, so that was the first time that was a confirmation that gravitational waves existed. The experimenters that built LIGO ended up the laser interferometer. These laser interferometers ended up winning a Nobel Prize for that discovery. Is quite a splash. But then, 2 years later, they detected the first. They detected the signal from the first signal of two of these compact objects, these neutron stars, spinning around each other and colliding. And you can see on the bottom here, this is a periodogram showing the frequency of the signal that they saw versus the time. And you can see that at negative 10 seconds before this merger time, there were two objects that had 1.5 times, both 1.5 times the mass of the sun, rotating around each other at 50 times per second. So there's just a crazy amount of the speed associated with that, the amount of energy associated with that. And then as time went on, that frequency kept increasing. So they spun up, and then eventually the signal disappeared. And so the idea is that they merged together, and then there was this 2 seconds of quiescence where nobody saw anything. And then our satellite, the Fermi Gamma Ray Space Telescope, that's currently in orbit and is monitoring the entire sky in the gamma rays, saw this spike. So it was the first confirmation that that theory going back to the 90s was true, that these short brief flashes of gamma rays are due to the merger of two compact objects. And so this detection kicked off an entire slew of observations, both on the ground and on Earth. The satellite that I was talking about, Fermi, is capable of sending out an alert to the ground right away. So the text shown here on the right, on the left is kind of what we receive on the ground. It tells us, hey, just right at this time, I detected something of this significance and this part of the sky. And so we got that immediately, and then 45 minutes later, the LIGO Observatory let us know that they actually saw something, and then about 5 hours after that, we were able to get all the data to the ground, combine the data, and figure out exactly where it was coming from. And so the sky map there on the right shows kind of like the overlap of all the instruments that detected it, and there was this like green banana shape that was about 30 square degrees in the sky. And so we released that to the community. There are a couple of different channels where astronomers now can can release these types of detections and alert other astronomers that we saw something. And so the idea was that anybody who had telescope time should go and look at this area of space and try to find where this thing came from. Like I said, 30 square degrees still has, there are tons of galaxies within that region, but the good thing is that the gravitational wave observatories could tell us exactly the distance that this thing was at. So, using galaxy catalogs, people could figure out which galaxies could be candidate hosts for this thing, and so both satellites in orbit and telescopes on the ground went and looked at each of those galaxies, and within about 12 hours, people were able to determine to detect the actual source. And so you can see the thing on the right there, and the upper left there, is the galaxy plus this new source that wasn't there from catalog images. And so that little blob on the upper left of the galaxy, of this elliptical galaxy, is the actual source. And then we had space-based telescopes look at it. Eventually, 5 days later, Hubble was able to get onto it and see the explosion. X-ray telescopes looked at it after that. So we were able to get a ton of data and work out the physics of like what was actually happening with this. There were instruments on every continent that ended up observing this thing, including space-based instruments, including a telescope, a neutrino telescope down in Antarctica. So it's pretty neat. And I could show, we had NASA put together an artist rendering of what this thing looked like. So these are the two objects rotating around each other, and the moment they merge, they form a jet that gets shot out. And so you get this jet that's producing the gamma rays, and so very dramatic. You have a black hole formed, and then a jet that gets produced, and then that jet propagates out and then produces the gamma rays that we end up seeing. So yeah, it was, like I said, a big hit in 2017. And then in 2020, NASA has every 10 years we do what we call a decadal survey, and where we go out and we commission a study by the National Academies to tell NASA where they think we should be aiming for science for the next decade, and they found that that this detecting more of these types of events is warranted, and there's lots of great science that we were able to do. I mean, some of that science was from this single detection. We were able to do things like measure the speed of gravity, which isn't something we usually think about. Like, but it's how quickly can gravity influence other objects. It's always assumed to be the speed of light, but it's never been measured because we didn't have those capabilities on Earth. But seeing gravitational waves and light come in at around the same time we were able to after traveling millions of light years, we were able to put a estimate on the speed of gravity, which essentially it's consistent with the speed of light. We were able to do things like measure the expansion rate of the universe, measure how stiff those the neutron stars are, so the state of the matter that's inside those stars. Look at the physics of how these jets are formed and the structure of the jets, and then most interestingly, how heavy elements are produced in the universe. And this one really was pretty unique, because we know that all of the elements in the periodic table up until about iron and nickel are produced inside the cores of stars. So as a star fuses hydrogen into helium to release the energy that we see in our sun. So our sun has a core full of hydrogen, and the gravity of the star is pushing those hydrogen atoms together. They fuse together. to form helium. Once it's done, once it's run out of hydrogen, the star will contract, and gravity will push the helium atoms together to form carbon, and carbon forms oxygen, and so on. And you go up the periodic table until you get to iron, and then iron, forming two iron atoms into nickel, actually sucks energy out of the star. So once that happens, that's when the supernova process takes over, because essentially the fusion process is no longer giving the star energy, it's taking star energy away from the star. And so where do all the elements after iron come from then? And so there have been lots of theories about this. The supernova itself is energetic enough that it produces some elements, but not enough to explain the amount of, even here on Earth, where does uranium come from? These plutonium, things that are way beyond iron on the periodic table. And we see much more of that even on Earth, and then also in the atmospheres of other stars and in the universe than could be accounted for just by supernovas. And so it was long predicted that the merger of these neutron stars might be a way to do this, and we did see the production of heavy elements from these stars, and so from this event, so it confirmed that theory. So all of this to say, with the decadal survey, that this was the motivation for the mission that I ended up proposing in 2020. It was selected by NASA that year, and we've been working on it for the last 5 years to get it ready for launch, and it's currently assembled and undergoing environmental tests. We shake it to make sure it's going to survive launch. We put it into a vacuum chamber and heat it up to make sure that the electronics will survive in space. And all of that is going to end and be done in September, and we're going to be ready for launch after that. And we're currently working with to get a launch to get into orbit after that. So with the time that I have left, I can talk a little bit about the mission and some of the fun, the engineering side of things. I'm a scientist, so I came into this looking at data and doing analysis and of the data collected by other satellites. So then getting into this role of working on building a mission allowed me to put on more of an engineering hat, which is fun. I'm somebody who is torn between going into physics and going into engineering when I was in college. And so to be able to kind of work with the engineers to develop new instrumentation has been a lot of fun. So the satellite itself, we had a couple of requirements that kind of dictated the design that we ended up having. We need it to be have a large collecting area. We want to be able to detect a lot of these things. We want to be able to measure individual photons coming into it, and we want to know exactly when those things arrive compared to clocks on the ground. And we want to so that influences the type of technology we want to fly, and I'll get to that in a second. We don't necessarily want something that's a light bucket that's just going to collect light. Like if you think about a space telescope like Hubble, it works like a camera. It opens the shutter and it collects data. And it's just like if you were exposing film, if you want to collect as much light as possible, you just expose for as long as possible, and then read that information out. And it doesn't matter which photon arrived first or second. It's just you're developing an image. For us, we want to have that time sequence, right? The light curve, and so we want to be able to measure each photon when they came in and time tag it. And so we want to have a detector that reacts every time a photon arrives. We also want to be able to tell where it came from. So this influences the shape of the instrument. We have to have a segmented instrument that looks out in different parts of the sky, and then based on how bright the different what the signal is in the different detectors, you can then back out where an explosion came from in the sky. And then, of course, we want to get it down to the ground. We want to get the information down to the ground as quickly as possible, because we want to tell other astronomers to go and look for this and do similar types of observations that they did for this last event that happened in 2017. And so that dictates the type of communication that we end up using. So these are the 6 like high level requirements that we have for the mission. You can see the image there that we ended up, the design we ended up putting together. It's an instrument that's a 5-sided box that's on top of a commercial satellite that we have an external spacecraft vendor developing for us. Let's see, so you go in, zoom in on the instrument itself. So the way a gamma ray detector works is that unlike optical light, for a telescope, for Hubble, they have mirrors and they focus the light onto a detector plane, onto basically what they use now are these charge coupled devices similar to what's in like an iPhone camera, right? So they want to focus all the light from over a large area onto this little detector, and then take that image. For gamma rays, you can't really focus them, so they would just pass right through a mirror or something like that. So you have to be able to stop them and collect the energy that they have. And so the way we do this is we use what are called scintillation crystals, and these are basically a form of salt. We're using cesium iodide, but sodium iodide is another common one, and those crystals have a lattice structure that when a gamma ray comes in, it interacts with the atoms inside that lattice and knocks electrons around, and the gamma ray ends up getting captured, and then the electron will eventually, that it energized and is now moving around the lattice, will eventually get captured by an atom, and it'll release its energy as optical light. And the optical light is very easy to detect. So what we end up having is an optically sensitive photoreceptor on one end of the crystal that can register when a gamma ray passed through it. And so every time a gamma ray passes through it, the crystal lights up. You could see this with the naked eye in a lab, for example, and the detector tells us and registers, okay, a photon just arrived and it was this bright, and it gives us the energy of that photon. And then we have 12 of those around segmented around a box, like I said, facing different directions in order for us to be able to tell where they're coming from. And then we put that onto the spacecraft. It has, let me see, I think this is a better view of it. Spacecraft has deployable solar panels. It's meant to, this ring is meant to attach to the side of something like a Falcon 9, like a SpaceX launch, where we're going to be a ride share, where they have now the capability to launch multiple satellites at once. So the idea is that we would attach to the side of inside the housing of the rocket with a bunch of other ones and launch all together. And yeah, this is the view of it stowed, connected to this launch ring, and before, and then eventually once we get into orbit, they would bounce us off. There's actually this ring that's shown here on the right, has a spring mechanism that allows us to gently kind of bounce off of the spacecraft and then go off and deploy the solar panels and begin operations. Just to give you a couple of photos of the actual hardware, this is the crystal that captures the gamma rays. We wrap that into in a reflective foil that's seen on the right here, in order for the optical light to get bounced around out to this exposed edge where the photoreceptors are. We wrapped it up. We put some cushioning on it. These are the chips that actually read out, or that can detect the light that's coming out of these things. These are just like the solar cells that you would see on a solar powered solar powered calculator or something like that. They're just very sensitive, and they will give a voltage out per photon. So that's kind of what we need. We want to get individual signals for each photon. And then this gets connected into what we call the SIPM tray, the silicon photomultiplier tray. And each of these detectors gets built and compressed and loaded so that they survive the vibrations for launch. And then those trays are added on to the opening of those detectors in order to read out the optical light that gets produced. There's another view of that with the window there on the right, and then we have the structure, the five-sided box structure. In each of these sides, we've put copper plates so that gamma rays can't enter in. Copper is very good at blocking gamma rays, so this prevents gamma rays from coming in from the back, because we want to preserve the directionality of the detectors. So the detectors have the capability to know which direction the photons came in, the light came from when it detects a gamma ray. There's some technicians working on installing the first of these detectors onto the structure, and this is the base plate that attaches to the spacecraft. It's a very hefty, big plate that's all machined out of a single piece of aluminum. It gives you an idea of how many fasteners go into this too, right? Just the amount of holes in this thing in order to keep it together to survive the vibrations of launch. And then this is the electronics box that powers everything. We have on the bottom there's the flight processor that reads out all the data. On the right, the electronics that measure the signals from these individuals photocells, and turn those signals, or analogs, they convert them into digital signals and send them over to the flight processor. And then that's the combined integrated box for the instrument. And then this is us taking it out at Marshall and getting it ready for environmental testing. So that's me on the right there, giving me the thumbs up that we've managed to successfully put it onto this, what we call a Flowtron. It allows us to manipulate it, kind of work with it. So you can see flipping it over to install some electronics. Yeah, so it's like 100, it's 150, so it's 300-pound instrument altogether, because the crystals are incredibly dense, because it's the only way they can stop the gamma rays effectively is that they're just very massive. So this thing definitely requires some hefty handling. So then, yes, it just looking at the harnessing that goes into all 12 of these detectors are connected into the central electronics box, and then another technician installing some of the final cabling, and then the closeout on the right. And then the checkout, and we got the thumbs up that everything worked there. And then just a quick series of photos. This is the vibration testing. We took it over and simulated launch. So we shook it in a way that would simulate the stresses that it'll see in launch. Survived all that, fortunately, so that all worked out. And then at Marshall, we also have a vacuum chamber that we put the instrument in. We pumped out all the atmosphere and went through cycles of hot and cold to make sure that it will survive as it goes behind the Earth and in front of the Earth. You get these huge swings in temperature. So we want to simulate that on the ground to make sure that everything will work once we get up there. And this was almost a month process of it being in there and going through this. I think it was close to a little over 3 weeks of testing to make sure that that there weren't going to be any bad solder joints or anything like that could fail once we get up there. There's just a few pictures of the engineers kind of setting this all up. Yeah, this is getting the data out of the vacuum chamber is quite a challenge. Just tons of electronics. This is pretty new. It's my first experience with working with these vacuum chambers. So took a bunch of photos of kind of what I thought were the kind of neat workarounds to these problems. Because like if you have a vacuum, how do you get data out? You can't just run a cable. So there are all kinds of these connectors that people use. Then some scientists looking at the data coming out. All of that worked out well. and that's the chamber that it was in for the 3.5 weeks or so. Yeah, I like this a couple of photos of just like, you know, it was so cold at the edge of this vacuum chamber because they were pumping in like liquid nitrogen to keep it to bring it down in temperature, that there was a lot of condensation forming around it and stuff. Let me go through, kind of getting short on time, just a picture of us sending it now up to Toronto, which is, there's a company there in Toronto that developed the spacecraft bus for us. They're connected to the University of Toronto, so a bunch of students there kind of have a lab where they work with the aerospace engineers, faculty there to develop low-cost spacecraft that can host these kind of instruments. And this is the final product. So this is now the satellite with the instrument on, the spacecraft bus, and the solar panels deployed. And then in the right is the stowed configuration. And so, like I said, now we're taking that whole thing and next month putting it through a combined vibration test. We're going to vibrate the whole thing, and then we're going to redo the thermal vacuum chamber testing for the entire spacecraft, for the integrated system, to make sure that it all works as expected. And then in August and September, that time frame will be complete and it'll be ready for launch. So it's been a 5-year process to kind of build that, to get more data, to do more of the science that we started back in 2017. With that, I'll stop there and take any questions that you guys have.